Hi students, in today's video we are going to discuss about coherent and incoherent addition of waves. Coherent and incoherent addition of waves is what is our next video. So what I would like to tell you is that consider a transverse wave. This part is called a crest and this is called a trough. Now we let another wave also to be superimposed over the first wave in such a way that this is the crest of the second wave. They are of same phase and same. Their wavelength is lambda. This wavelength is also lambda. So what do we get here? In such an addition, so this is 2. So in this superposition, the crest of one wave is superposing to the crest of another wave. So this is A. This also is A. In such a superposition, we will get a resultant wave like this. Right? The same wavelength is 2A. This is minus 2A. Because here what is happening is the crest of the first wave superimposes with the crest of the second wave. The crest of the first wave is superimposed over the crest of the second wave to the maximum. And so this kind of superposition is what is called constructive interference. Constructive interference. What do you mean by constructive interference? It is that interference where the crest of the first wave is superimposed over the crest of the second wave and the trough of the first wave is superimposed over the trough of the second wave. In that case, the resultant wave will give us a maximum. The resultant amplitude is 2A, between plus or minus 2A, I can say. Now let us take the second case. So here, what I am saying is that this is the crest of first wave. So this wavelength is also lambda. Now we will add another wave in which what I am saying, this is crest, this is trough, right? So in this case, what is the outcome that we are going to get? What will be the outcome of this one? Suppose this is amplitude A. We are considering waves of same amplitude minus A plus minus A. So the result is going to be 0, right? In this case, the result is going to be 0. And this kind of interference is called destructive interference. Destructive interference. This is called the destructive interference. So my question, how will you define destructive interference? How will you define the term destructive interference? It is that interference in which, it is that interference in which the crest of one wave is superimposed over the trough of the second wave. So why is it called destructive? Okay, once more I will give the definition. That interference where the crest of the first wave is superimposed over the trough of the second wave. Crest of the first wave is superimposed over the trough of the second wave. In this case, the result is a minimum. Right? In the former case, we got a maximum. In constructive interference, we get maximum. In destructive interference, you get a minimum. Right? In constructive interference, you get a maximum. In destructive interference, you are getting minimum. Right? So these are the two types of interferences you have to understand. So constructive interference and destructive interference, the two types of interference you are going to learn. Now we will consider the cases of this. Let us consider different wavelengths. The dotted lines show the trough and thick lines show the crest. So every wave is having an alternative crest and trough superimpose the first wave and the second wave. You can see here. Okay, what is the superposition? This is maximum. Capital I am saying maximum. This is maximum, 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 right? Then minimum, minimum. Okay, maybe my drawing irregularities is there, so they should come in a like minimum. Again, minimum. So you can see here, you're getting a set of maxima like this, you are getting a set of minima like this, you are supposed to get. So this is what I can say regarding the constructive difference and destructive difference. Now, in understanding this concept in more detail, let us consider light from source. This is source as well. The light from the source is traveling. Yes. Lambda, 2 lambda, 2.5 lambda. The distance traveled, the distance P, S1P is equal to 2.5 lambda. Right? Now I got another one S2. I will consider S2 somewhere below. Okay, both wavelengths are lambda here. This is lambda. So lambda, 2 lambda, 3 lambda, 3.5 lambda, right? So S2P is equal to 3.5 lambda we are getting. S1P is equal to 2.5 lambda, S2P is equal to 3.5 lambda. So may I ask you a question? What is the path difference here? What do you mean by path difference? Path difference means the difference in path. In this case, the path difference is equal to 3.5 lambda minus 2.5 lambda. That is equal to lambda, and in this case you can see that both waves are superposing in the same phase, right? Both waves are superposing in the same phase. That is, phase difference will be either 0 or 2 pi or 4 pi, likewise, right? So in this case, the phase difference is equal to 2 pi because there is a path difference of lambda. There is a path difference of lambda, they will have a phase difference of 2 pi. This is 1 wave, 2 wave, 3 wave, 3.5 wave. This is 2.5 wave. That means 2.5 cycles are over here. 3.5 cycles are over here. That means there is a phase difference of 2 pi. Here 2.5 circles. Here 3.5 circles. A difference of 1 circle you can observe between them. 1 circle means phase difference 2 pi. So phase difference here is 2 pi. Path difference here is lambda. In this case you are going to get a maxima, right? In this case you are going to get a maxima. Now let me consider the next equation. So this is S1P. So this S1P is equal to 2 lambda. And the point is 2 here. Now what is it? This is lambda, this is 2 lambda, 2.5 lambda. So S2P is equal to 2.5 lambda. Now how are they superposing? The first wave reaches in this one. Second wave reaches here in this one. That means they are superposing in the opposite sense, right? So here the vibration, here the wave is downwards, here the wave is upwards, correct? They are superposing in the phase difference of I. So here phase difference is equal to pi. In other words, one can say the trough of first wave combines with the crest of the second wave, right? the trough of the first wave is comparing with the crest of the second wave, do you expect a maximum or minimum? Tell me please, tell me, please. When crest of one wave superimposes the trough of the second wave, are you going to get a maximum or minimum? No, it's a straightforward answer. The answer is going to be a minimum. So here the path difference is equal to, so what the path difference is equal to? 0.5 lambda. You are going to get a minimum. Here the path difference is lambda, you get a maximum. Suppose if the path difference is 2 lambda. If the path difference is 2 lambda, if I make one more wave I am adding, such that I am taking S1 to this point. S1 is now here. S1 is here. S1, sorry, S1 not S1. S2 is here. So in this case, S2 is equal to 4.5 lambda. Path difference 2 lambda. 4.5 lambda minus 2.5 lambda is equal to 2 lambda. Yes, what are you going to get? You are going to get a maximum, right? You will get a maximum here. And in this case, what is going to be the phase difference? 1 circuit, 2 circuit, 3 circuit, 4 circuit, 4.5 circuit. 1 circuit, 2 circuit, 2.5 circuit. Path difference, a difference of 2 circles. A difference of 2 circles means 1 circle has a phase difference 4 to 5. 2 circles has got a phase difference 4 pi. 4 pi. The difference, phase difference is 4 pi for 2 circles. Right? I mean circle because one wave completes a cycle. Cycle is what I mean a circle. So one wave means one circle. 2 wave means 2 circle. 3 wave means 3 circle. 4 wave means 4 circle. 4.5 circle. 1, 2, 2.5 circle. Difference of 2 circles. Path difference 2 lambda. Phase difference 4 pi. That means a path difference of lambda is equal to phase difference 2 pi. A path difference of 2 lambda is equal to phase difference 4 pi. A path difference of 3 lambda is equal to phase difference 6 pi. Right? I hope this is now clear. I hope you are getting all these ideas perfectly. Right? So this is how we are getting into this situation. So now we are able to consider this. So here 2 circles, 2.5 circles. Now if I add one more wave here, I won't make a change in the answer, right? In this case, the S2 is equal to 3.5 lambda. In this case, it is 1.5. This is 3 pi. 1.5 is 3 pi. You will get a minimum. What does that mean? That means condition for obtaining maximum. Condition for obtaining maximum is phase difference is equal to 2n pi and path difference is equal to n lambda. Here I take the value 0, 1, 2, 3, etc. to n lambda. You can see here. For putting n is equal to 0, path of phase difference 0, you get a maximum crest and crest superimposes. Phase difference n is equal to 1, phase difference 2 pi, again you get a maximum. If you put n is equal to 2, phase difference is 4 pi, again you get a maximum. N is equal to 3, 6 pi, again you get a maximum. Correspondingly, n is equal to 0, no path difference, maximum. N is equal to 1, path difference, lambda. Lambda, path difference, lambda, again a maximum. Again, n is equal to 2, path difference 2 lambda, again you will get a maximum. N is equal to 3, path difference 3 lambda, again you get a maximum. So, condition for obtaining a maximum is like this. In the similar way, the condition for obtaining a minimum is phase difference is equal to 2n minus 1 pi, where I take the values 1, 2, 3, etc. Textbook has slightly different answer, but I will tell you study this only because the other thing will confuse you, that I will explain along in my class. And correspondingly, path difference is equal to 2n minus 1 lambda by 2. Again, n satisfies this condition. This is the idea regarding the addition of what is called coherent waves. Now one thing we got about coherent waves in all these discussions is that the waves that we are using must have same wavelength, isn't it? The waves that we are using must have same wavelength lambda. So now we need to define what is called coherent waves. We have learned this in first year. So we can define coherent waves as waves having same wavelength comma same frequency and constant phase difference between them. Constant phase difference. Constant phase difference between the waves. So waves having same wavelength, same frequency and constant phase difference between the waves are termed as coherent waves. An important point I have to highlight here is that two independent sources of light, cannot be coherent. Cannot be coherent. Two independent sources of light cannot be absolutely coherent, I believe, because condition of constant phase difference cannot be attained. Condition of constant phase difference cannot be attained. So, two independent sources of light. So, an important sentence is this: two independent sources of light never form coherent sources because the condition of constant phase difference cannot be attained. Why? Because as you have studied in chemistry that generally radiations are produced by atomic excitations and excitations. So if all are happening at the same time in two independent sources, then only we will get that constant phase difference, which is practically impossible. That's the reason why we say two independent sources of light can never be coherent. So now we will consider the mathematical analysis of the coherent addition of waves. Let y1 is equal to a cos omega t and y2 is equal to a cos omega t plus phi represent two coherent waves at x is equal to 0. You can see coherent waves because phi is the phase difference between them. And considering their amplitudes are same, it is not necessary for coherent waves that they must have the same amplitude, but here I am considering they have same amplitude. According to our knowledge, the resultant equation y is equal to, or before that we will expand this expression. This is a2 cos omega t cos phi minus a2 sin omega t sin phi, right? Sorry, instead not a2, it is a itself. Now add these two equations, what do you get? Cos a cos b cos phi, right? Adding these equations, I am going to get y is equal to what? A into 1 plus cos phi into cos omega t. Right. Then minus a sin phi sin omega t is equal to. So a into 1 plus cos phi sin phi sin omega t, which can be written as small a cos omega t plus theta. Okay, before that I will do one more thing. Then you understand. Let small a cos theta is equal to capital A into 1 plus cos phi. And small a sin theta is equal to capital A sin phi. In that situation, we get y is equal to small a into cos theta cos omega t minus sin theta small a into exponent taking outside sin theta sin omega t. And then we got the similar form that is equal to small a into cos omega t plus theta, right? Small a into cos omega t plus theta, because why I am doing this is I want to make the equation of the resultant wave also similar to that of the incident wave. Now we are getting the equation like this. Now this is equation number 1, this is equation number 2. So what is equation 1 square plus equation 2 square will give you? Equation 1 square plus equation 2 square will give you. Left side is a square, because a square cos square theta plus a square sin square theta. Cos square theta plus sin square theta is equal to 1. That is equal to capital A square plus square is a square cos square phi plus 2a cos phi plus a square sin square phi. R square we added. Now we can see one more thing from here. What is this a square cos square phi plus a square sin square phi? Adding these two terms. Okay, with your permission, I am just taking this part closer. And then I will write everything 2a cos phi. Now we can see that this is a square cos square phi plus a square sin square phi is equal to a square plus a square plus 2a square plus 2a or a square, let me see here. A square, right? It's a square. 2a square cos phi. That is 2a square into 1 plus cos phi. What is 1 plus cos phi? This is 4a square cos square phi by 2. 4a square cos square phi divided by 2, that is the value of small a square. Let me tell you. Small a square is equal to 4 capital A square into cos square phi divided by 2. Okay, so now according to your knowledge, the intensity of a wave is directly proportional to square of the amplitude. In that case, I can say or I is equal to alpha, and alpha is a constant into small a square. I'm going to multiply both sides with alpha. Let us take this is equation number 1. So alpha into small a square is equal to 4 into alpha into capital A square cos square phi by 2. What is A? A is the amplitude of each wave, amplitude of each source. A is the amplitude of each source. So I will now say alpha A square. Alpha A square is I. That is the resultant intensity. That is 4I0. I0 is equal to alpha A square intensity of each source. Intensity of each source. 4I0 cos square phi divided by 2. The resultant intensity I is equal to 4I0 cos square phi by 2. Phi, what is phi? Phi is the phase difference between the two waves. Phase difference. Phi is the phase difference between the two superposing waves. So I am getting I is equal to 4I0 cos square phi divided by 2. Okay. 4I0 cos square phi divided by 2. That's the result in English. So I am writing that once more. 4I0 cos square phi divided by 2. From here, what is I max is equal to maximum intensity. Maximum intensity means this term is equal to 1. That is 4I0. What is I minimum is equal to? Minimum means this function is minimum. Cos square. That is equal to 0. That means what is I average is equal to 4I0 plus 0 divided by 2, which is 2I0. So what I can say is that the average intensity still remains a constant, right? 2I0. What is I0? That is I0 plus I0. I0 is the intensity of the first source. The second I0 is the intensity of the second source. That means the total intensity is still conserved. Intensity means energy per unit area per unit time. That means energy is conserved. So I have to say interference of waves is on the basis of the conservation of energy. It is on the basis of the conservation of energy. The interference of waves is on the basis of the conservation of energy. So in interference, energy is always conserved. In interference of waves, what you have to understand is that the energy of the wave is always conserved.